Yay!
Yay! All right, so let's see how masses act under the influence of a restoring force, or a spring force, or a rubber band, or anything that tries to restore the mass back to its original position. Okay, so the classic case is I've got a mass on a spring, and what I'm going to do is I'm going to pull this mass out some distance away over here. Suppose that's the same thing. And I pull it this direction, some delta x. Well, what's going to happen? You know, if this was a spring or a rubber band, you sort of know what's going to happen is that there is a force that acts back this way. Spring force. I guess this would be a vector, right? In general. Okay, so I've got a spring force that's trying to pull it back the way it was. And likewise, if I had pulled it this way, if I compressed the spring, it doesn't work so well with rubber bands, right? Then the spring would try to restore it back to its position that way. So basically what happens is that whatever displacement the mass undergoes, whatever direction I try to push or pull the thing, the spring tries to resist me, right? The force is in the opposite direction. So what we say is that this spring force is minus some constant. This is called the spring constant. It's not a very inventive name. Times the amount that I displace the thing. The negative sign just means that it's in the opposite direction. So if I try to stretch it to the right, it pulls back to the left, right? So that's what all that means. The K is in units of newtons per meter, right? If you just divide the x on the other side, that's got to be newtons per meter. So it kind of makes sense that this is like the stiffness of the spring. If it's like 20 newtons per meter, that means in order to stretch out the spring 1 meter, I'm going to have to apply 20 newtons to do it. So the bigger the K, the sort of the stiffer the spring. Okay, so what we do is, if this is the only thing acting on this mass, so forget about friction or gravity, it's on a horizontal surface. If friction is the only thing acting, and it's all in one direction, so I can sort of forget about that vector sign, that means, if I apply Newton's law to this thing, that means that this force, this minus K times the amount, x, let's say that I stretch it, this is going to be equal to ma, mass times its acceleration, how it accelerates. All right, so what I can say, this implies that a is just minus k over m times x, but I can write the acceleration in terms of the x. Remember that the acceleration, that's the second derivative of position, right? V is dx dt, a is the second derivative, d squared x dt squared. So I can write like this. D squared x dt squared is equal to minus k over m times x. I can write it like that. I'm going to use just a little bit of physics notation. In physics, remember things like velocity, acceleration, those are all with respect to time. And we do that so often that just to save writing, we write that in sort of a special way. It looks like this. Each derivative with respect to time, we just put a dot over the x. Like you might have seen in calculus or something where you have dx dt, or like dy dx. Sometimes in calculus books you see that as y prime. Have you ever seen that? That's we can save that for taking the derivatives with respect to something in space, like x. In physics, we want to make time a little bit special. So usually what we do is we just put a dot over the thing instead of a prime, but it's just notation, just to save writing. Okay, so I can write this as x double dot is the way that it's pronounced, and this is minus k over m times x. Okay. Now what we're trying to do is we're trying to find what function of x, right, that describes the movement of this thing. What function of x is going to work? And what this is saying is I need some function, x is a function This isn't an algebraic equation where I'm trying to find x as a number. This is a differential equation. So I'm trying to find x as a function. So what function could there be where I take its derivative twice and I get the original function back again with a minus sign? Right? Well, you might guess. This is one way we can solve this. You might later take courses in solving differential equations. But one way we can go about it right now is just to be good guessers. So we can guess and then check. So one thing we can do is just guess. What function, if I want to differentiate a function and then get it back again, one choice would be, let's try, this has got to be a function of time, right? So let's try in fact, let's be a little bit careful. Let's try e, because there could be a constant up there. We'll talk about the constant in just a second. Just for kicks, let's call this constant omega. E, the omega t, right? So that means that x dot, if I take the first derivative with respect to time, what do I get? I'm going to get a omega e, the omega t. Okay, and if I do it again, I'm going to get, pull the omega down again, so I get omega squared e to the omega t. Well, look, that's almost what we've got, except that omega squared is guaranteed to be a positive number, right? And we need to have a negative sign out in front there. K over m has to have a minus sign in front of it. So that doesn't quite work. And then you think, oh, maybe I'll try this. Maybe I'll try e to the minus omega t, so that I get a minus sign here. But then that doesn't work because, oops, that's a minus 2. Because when I do another derivative, then I get a positive sign again. So this is promising, but it doesn't quite work. But then you might remember from calculus that sine and cosine are interesting because if you take the derivative twice, you will get the original sine or cosine back again, except that you also get a minus sign, which is exactly what we want. So let's try this. So this, that makes us sad. That doesn't work. But let's try. I can put a constant out front. That's going to be what we call the amplitude. Just because when I take a derivative of cosine, that a just comes along for the ride. It doesn't really do anything. So I'm free to put the a in there. Okay, so a cosine omega t. Let's try that. Now, why isn't it just cosine of t? The reason is because you know what has to go in there. You can't take, if I said, what's the cosine of like 5 seconds? It doesn't make any sense. There is no cosine of 5 seconds. Whatever's in there can't have any units, right? Or it's got to be degrees or radians or something that are basically unitless, just fractions of a circle. So cosines just work on angles. So what's the cosine of 5 meters? It doesn't make any sense. There is no cosine of 5 meters. It's undefined. So t has units of seconds. So in order to get a sensible unit in there, like radians, I'm going to have to multiply the t by something so that I get a unit of radians out. So this thing, this omega, must have units of radians per second, because when I multiply by a t, then I just get radians. And that's the old radians per second. That's like an angular speed, right? You've seen that before somewhere, maybe in a math class. So that's the right thing. That omega t gives us an angle. All right, so let's see, x dot. By the way, what is x dot? That's the velocity, right? Derivative with respect to time. And this is, well, when I take the derivative with respect to t, what do I get? I get a minus omega a sine omega t. Neat. So that's the velocity at some time. And then if I do it again, I bring out another omega, right? And then flip the sine to cosine. And so then I get minus omega squared a cosine omega t. But that was just our original x. So we've done it. We found something that works. And the nice thing about these differential equations is once you found something that works, you're done. There are uniqueness theorems. So if I found something that works, I don't have to worry about, oh, maybe there's a whole bunch of different functions that work. Nope, this is it. I mean, cosines work, sines work, and if I add them together, I can get something else that works. But if it's a what's called a second degree differential equation, so if it's two derivatives, then I'm going to have two solutions. So I'm going to have a cosine and a sine. Either one work. We're going to stick with the cosine. All right, so this works. Cool, this solves the equation. So the way that this thing moves, which shouldn't be an enormous surprise, the way that this thing moves is going to be a cosine omega t. And then if I were to draw this out, I mean, you sort of know what this looks like. If this is t, and this is x, what happens when t is 0? When t is 0, what's the value of x? It'll be cosine, then cosine of 0 is 1, right? So x is just going to be a. So this is going to be the position a up here. So we start there, and then cosine sort of does that. Okay, and this a is what we're going to call the amplitude. It's sort of the initial position. It's how far I've stretched the thing to start out with. Since cosine only varies from -1 to 1, the amplitude just multiplies the whole thing, so that it can vary from whatever to whatever, whatever your amplitude is, whatever the initial position is. Okay, let's see. Oh, if this works, notice what this means. Look at this factor right there. That omega squared is our k over, well, I guess I have a minus sign, right? That omega squared is just k over m. So that means that our angular frequency is just the square root. We're going to use this over and over and over again. It's just the square root of k over m. And what is angular frequency? That's radians per second. A lot of times what we're going to want is not radians per second, but we're going to want frequency, which is cycles per second, also called hertz. So the relationship is, if I know how many cycles per second something is, if I multiply that by 2 pi, then I got it, right? Because there's 2 pi radians in one cycle, going all the way around like in a circle. So we know, it turns out to be true that, you might not know it ahead of time, that the angular frequency omega is equal to 2 pi times f. And the way that the units work out, it's 2 pi radians per cycle times frequency is cycles per second, right? And so we get omega as being radians per second. So omega is 2 pi f. Cycles per second is also what we call a hertz, is the shorthand for it. So a lot of times they're going to be interested in frequency, because that's really something you sort of measure, and then you convert into omega. Another thing we do is, instead of the frequency, instead of the cycles per second, maybe you're interested in the seconds per cycle. The inverse of frequency is called the period. How long does it take to do one cycle? So frequency is 1 over the period, t. Usually t is used for period. So that means that t is just 1 over f. And so that'd be 2 pi over omega. And so that would be 2 pi times the square root of, I'll just flip the omega, m over k. Okay, this is another one that we'll be using quite a bit also. All right, and so just to get a feel for how all this stuff works, as an example, a 1 kilogram mass attached to a, let's see, what kind of spring should we use? Let's do K is 100 newtons per meter. That's the stiffness of the spring. So what would the period of such a thing be? How long would it take for this thing to undergo one cycle, one vibration? T is 2 pi times the square root of m. Let's see, it's just going to be 1 over 100. Square root of 1 over 100 is like 1 over 10, right? So it's just going to be 0.63 seconds. Just twice pi over 10, 0.63. Just move the decimal point. So that's how long this thing is going to take to undergo one cycle, to undergo one full back and forth vibration. And then we can say, where is it? I'll try to do this right here. Let me carve out some space. Oh, I'll just go to the next page. Okay, where is it? After 2 seconds. So let's go back and find this thing's position after 2 seconds go by. Well, I know the position is given by a cosine omega t, right? Let's see, did I say, if A is 10 centimeters, so let's say we stretch this thing out 10 centimeters and then we let it go. So that's the amplitude, the initial position. So if this was at 10 centimeters, then this is going to be 10 centimeters is 0.1 meters times cosine omega t. Okay, we said omega would be, omega is the square root of k over m, right? So this is going to be 100 over 1, or 10. So this is just going to be 10 times 2. The time is 2 seconds. So this is going to be 0.1 times cosine of 20. And just to make the point, this is in radians, right? So make sure, up to this point, your calculators have probably been in degrees. So now you need to change over to radians. And if you do that, you should wind up with 0.04 meters. So 4 centimeters away from the equilibrium position. Okay, so we can forecast at any time in the future, we can predict where this mass is going to be just using these relationships. What about figuring out the speed of the thing? Well, that's going to be pretty easy, because the speed at any time t we said was just going to be minus omega a sine omega t. So if we plug values in, we should be able to find the speed at any point also. Okay, so that's the introduction to all of these variables that we'll be working with the rest of the unit.